Hello, welcome to the video, and in this video we will take a look at the stability of two-stage feed-forward opamp, and basically we will see that how far the zero must be from unity gain frequency, or how far the zero must be, or how far the zero must be on the left side of omega u or omega loop. So basically we have our opamp structure of two-stage feed-forward opamp, and let's see its Bode plot or its magnitude plot. So while only looking at stability, so this we can consider that we have an ideal DC gain, because anyway, even though in reality the DC gain is limited and not infinite, so that doesn't play a crucial role while defining stability. So let's take that this is ideal gain, and our point of interest is over these frequencies. So this is our omega u, and which is basically GM1 by CL, and our focus of implementation should be near this frequency range. So let's take k equals to 1. So we have, let's suppose that we are placing our op-amp in unity gain feedback loop, and so for our easiness, as we know that omega u lies at very high frequencies, so let's remove all the conductances, because at very high frequencies these will be short circuits. So like if we remove the conductances from the circuit, so uh, we remain with this kind of circuit, and where we can say that we have shifted our both of our poles to 0, so to the 0 point. So we can start our 20 dB roll off from here, not exactly 0, but we have shifted them way behind, and as there are no GO1 and GL, both poles will be near origin, and so thus we can derive our transfer function V naught by VE, which is GM1 plus GM2 by SC2 times GM3, and which is divided by total impedance by the output capacitor CL. So this is nothing but over here in this capacitor there are two current paths, from one from here and one from here. So basically this is from GM1, this is GM2, and this is GM3. So what we have is the current from here is denoted by GM2 by SC2 multiplied by GM3, and from here it is basically GM1, and both are further going through CL. So the output gain is basically divided by SCL. So now we can say that our gain, which is basically this equation, when we solve it further and bring it in a form of our analog template, so we can say that from here omega u, and we also know that omega u is GM1 by CL. So if we write in this form, so our Z1 becomes to be GM2 GM3 divided by GM1 C2. And now let's say we make a negative feedback loop with K, which is not 1, so it is basically greater than 1, and let's put the op-amp into it. So when we put this op-amp into it, so basically what we are doing is we are again driving a transfer function with including the negative feedback loop with a gain of k, and thus our transfer function will look like k divided by 1 plus k by a, and which is basically if we put the values of k, if we basically put the values of a from here, so this is what we will get, and thus our transfer function will look something like this. And this is basically the equation in the form in which we can compare it with the standard second order equation, and when we compare it, so this is our standard second order equation, and if we compare it, then our omega n, basically it is omega n and omega n squared. So omega n turns out to be omega under root omega u times z1, and our damping factor sigma is basically half root omega u by z1. And we know for critical damping, our sigma should be equals to 1. So thus, from over here, from this equation, we can understand that our z1 should be exactly equal at omega u by 4. And then we can get a critical damping. And this basically shows that our omega so sorry, R0 should be at some value which is omega u divided by 4. So it is at left hand side of omega u. So thus we can like this is analytically confirming that our intuition of 0 lying within the omega u is true. And over here we can understand that from this we can say if z1 moves to the lower and lower frequencies. So let's say now we have z1 somewhere over here, and if we make it move to the lower and lower frequencies, then the damping factor will increase. And if it approaches omega u, so it goes to the right side, so the damping factor decreases and ringing might happen. So let's talk about it further. So also we have to remember, when we analyze opamp as integrator, our non-dominant pole, which was p2, should have had light greater than 4 times omega u for critical damping. So we have some kind of symmetry in our results. So now what is the value of the location of the 0, and what value of z1 we should really choose? So this is a question. So is there any lower limit to shifting the 0 towards the left hand side? And let's analyze. So we know R0 is occurring at gm to gm3 divided by gm1 times c2. So if we want this 0 to shift towards the left hand side or the two lower frequencies, what we can do is we can play with these two factors, or we can play with these factor. We can reduce these, or we can increase c2, but we cannot play with gm1. And let's say we don't play around gm1 as it influences omega u or omega loop. So we have gm2, gm3 and c2 to play around, and we know the value of our omega u is gm1 by cl. Thus omega loop is gm1 by cl times k. Okay, so coming back to our circuit, we have a circuit, and we can increase the value of C2, or we can decrease the value of GM2 or GM3, or both. And in any case, the result is basically we have these three components we can play with. And in any case, the result is whatever the current is coming out from GM3, it is going to be reduced. Or let's say in Laplace domain, it is going to take time to build up. So this current will build up very slowly. And if we have a step input at the input, so let's say we applied a step input at the input of this topology, where this is our op-amp, which is placed in a negative feedback loop. And now initially v naught is at some value. Let's say it's at some value, and it won't change instantaneously as our v in, because let's say v in was at this value and v naught had some value. But now v in changes instantly, but v naught won't change instantaneously, and it is across the capacitor CL. So thus the feedback voltage won't change instantly. And also initially current coming from GM3 is very small. Thus initially we are having only the first stage of op-amp as working. And we can say that initially when the step is applied, the only stage which is working is our first stage of our op-amp, and our second stage is not working initially when the step input is applied, because the current is taking time to build up from the second stage. So like let's say 0 1 is at very small frequency. So let's say we have increased the value of C2 and decreased GM2, GM3. So the current, let's suppose that let it take time to build up. So the case we discussed just now. So let's take it that we shifted our zero to very small frequency by changing the values. And initially, the current through GM3 does not build up. So after a long time, the current through GM3 builds significantly. So what does this mean? So when we take a graph of voltage across time and we apply a step input Vi, so what happens to our output? So output will start rising, and it will start rising, and it will like in initial case, it will asymptotically reach the k times Vi stage. But we, as we know, due to the finite gain, we have some kind of steady state error. And now this is the initial case, and after some time, our stage two comes into the picture. After a long time, current through GM3 builds significantly and reduces the steady state error by giving more gain. How? So it pushes more current into CL, and thus the steady state is reduced. Steady state error is reduced. So this is what we get, but it's the matter of time. Like we have to wait for this kind of result. So even though DC gain is higher, but it takes time to reach at that point. So it is not beneficial to push the zero to very low frequencies, as it defeats the purpose of having high DC gain, due to the reason that we need to wait for that. And when we have step response inputs, basically the input appears rapidly, and as the op amp takes time to respond, feed forward op amp may not be the right choice when it comes to step input. So now let's see. Opamp has its upper supply. Oh, okay, sorry. So now I think we have laid a proper discussion on feed forward opamp when it comes to step input, and we have analyzed this case as well. So now let's discuss opamp on a macro level. And so now op-amp, when we look as a op-amp on macro level, so op-amp has its upper supply voltage, which is V plus plus, and op-amp has its lower supply voltage, which is V minus. And when we plot the V out versus V in characteristics, so it looks something like this, and we have the slope as DC gain, but it does not reaches till V plus, or it does not go to infinity, but it gets saturated at some value lower than V plus and some value greater than V minus, and that is called V saturation. And we usually determine what V saturation plus and V saturation minus are from the datasheet of the op-amp, and it's not necessary that these two values are symmetric. And thus V sat plus and V sat minus um, may or may not be equal, and this is a limitation of swing limits, which are the saturation voltages. And this can also be analyzed from the single stage op amp. It's not just the V naught which is limited, but also the current from the transconductor is also limited, or the output current is also limited. And how? So the current is limited means that as we go on increasing the input voltage VE, so the output current will go on increasing, but it will stop after a certain point and become constant. So let's say this is a V naught versus time curve. So we applied a VE input. So we have our V out in this direction, and its slope is basically the current divided by C. So now as we apply higher value of VE, so the current will increase, and thus the slope will increase. And when the slope increases, we have this curve. Let's say again we applied higher value of VE, again the current will increase, and thus the slope will increase, and thus we have this curve. But as we said, that there comes a point after which the current does not increases. So let's say that we have applied a voltage VE, which is a like which is a voltage after which we increase, which is a point after which even though if we increase the input voltage, the current won't increase. So let's say at that position, the current is Imax, and thus the slope is Imax by C. So now beyond a certain VE, the current does not increases. So, and this limitation is basically called as slew rate limitation, and it also has upper and lower limits for slew rate plus and slew rate minus. So it is denoted by SR plus and SR minus. So let's talk about it more. So if we apply a step input to a op-amp, which is placed in a negative feedback loop, so what will happen? So basically the input voltage will get instantaneously changed to delta V, and let's say we applied a input voltage of delta V. So what will happen to the output voltage? So it will initially start with the slope, which is basically GMV by C, and it will then reduce and asymptotically reach the K times delta V value. But when delta V is applied to the input, the output will start with a slope, like let's say over here, omega U times delta V, and then asymptotically reaches K dot delta V. So we have the equation, and let's say uh, we consider that as we go on increasing the input step voltage, so as we go on increasing the delta V, there comes a point where omega U times delta V exceeds the slew rate of the op-amp, meaning the slope exceeds the value for which Imax is attained. And at that point, even we increase the size of step, it it start with a slope equal to a slew rate, and then asymptotically reaches the gain value. Basically, the output is not linear with the input anymore after this point. So we said that input to the integrator is VE, and thus the output is V naught equals to omega U integration of V dot dt. But in general, this is not the case. So in reality, we have some errors, and those errors are due to V offset and V noise. So in reality, our V naught is basically equals to omega U integration of VE plus some errors which are limiting the value of integrator, and V off and V noise are given basically in the datasheet of the op-amp. Thus, the accuracy to which the feedback quantity tracks the input quantity is limited by the value of V off and Vn. So what more things do we expect in the datasheet? So there is a DC gain given, and there is a V naught versus V plot of DC, and there is a slew rate, and the slew rate is the function of V plus and V minus. And along with that, we have AC magnitude and phase response, basically a body plot. We have V offset and V noise. Along with that, we can also have maximum supply voltage, maximum load current it can take. So these are some things we will get in our datasheet. So most of the op-amps in the market are basically like dominant pole op-amp or Miller compensated op-amp, and there also are some op-amps which are unity gain compensated, meaning if the op-amp is connected in a unity gain feedback, it will give a stable output, or it will be stable. And in such kind of op-amp, we basically see these kinds of curves, and after omega U, the poles and zeros and whatever are there, they lie, and thus this basically gives the guaranteed stability for any k value. But here one compromisation we have to make, and which is our omega loop is always going to be lesser than omega U. So our omega loop is always going to lie at lower frequencies, and which means that basically if we increase the value of k, omega loop shifts to the lower value, and we pay a price by getting a lesser range of frequencies over which we had a significant gain. Because then let's say it omega loop comes over here. After this point, we will get a gain which is basically below the 0 dB line and which is not of our interest. So we'll get a lower bandwidth. So this is the price we pay for such kind of op amps. And to improve this, there also exists some kind of op amps which are for specific gain or greater than specific gain compensated. And this means that if op amp is connected in a gain which is k greater than some value, let's take over here that the value is 10. So if the op amp is connected in a gain k greater than 10 in negative feedback, it will always be stable. So how will it look? So let's say for unity gain, the curve will be something like this, where the poles will might lie before the omega u. But that is not of our concern because we said that the k value is 10 or greater than 10. But then when the value of k is 10 or greater than 10, let's say boundary condition is 10. So in such case, these are unstable for k equals to 1. But for k equals to 10 or greater than 10, they are stable. How? So their curve something looks like this. And then after reaching 0 dB, the poles and all lies after the omega u or omega loop. So this helps us getting higher gain as well as higher bandwidth. So I think that's all for today's video. Thank you.